the organizers for giving me the opportunity to close the conference. And I apologize for not being here in the days before. So, all right. So actually, I realized by seeing Kilian Rachel's talk that I'm going to deal with objects that he has also considered in completely different contexts. There's no probability in what I'm describing. It's only algebra. And I want to show you how this function, which I call quantum dilogarithm, it can be involved in understanding Macdonald theory. So a theory of Macdonald polynomials, and more precisely, thinking of polynomials. Well, there's various ways of actually defining them. So the historical way was as orthogonal polynomials with respect to a very special measure of many variables. Another was to realize that there were common eigenfunctions of some difference operators. And I'm going to go more in that direction. And those difference operators are actually expressible in terms of double affine Whittaker algebra and its representations. So all the work of Cherednik and others. But here I'm going to be actually concentrating on other solutions of the difference equations of which the Macdonald polynomials are solutions. Sorts of analytic continuations of Macdonald polynomials in their degree, right? So you think of a degree now as a complex variable, and that's going to be really the variable in which you analytically continue them. So this is a joint work with many people. We've been working on this for almost a year now via Zoom. So Renat Kedem, Junichi Shiraishi, Jean-Émile Bourgine, Misha Bershtein, and Vincent Pasquier. All right, so I'll describe the main character, which is this quantum dilogarithm. It's define it, give its properties, its various names. Define the notion of these Macdonald functions, these sort of analytic continuations of Macdonald polynomials. Explicitly work out the case of SL2. It's always a good idea. And in particular, in this case of SL2, it's very easy to understand the various dualities and representations that you have for these Macdonald functions. And then go to the general case, and if time permits, discuss Q operators and conjectures. Okay, so quantum dilogarithm. So what is called quantum dilogarithm is actually this simple infinite product here. So I call it E of z. In a previous talk, there was an E index Q of z, which is not quite the same, you will see. But it's kind of related. So for me, Q is a complex number, which is non-zero, probably of modulus less than 1 if you want things to converge. And why the name? Why is it called quantum dilogarithm? Well, if you look at the limit Q goes to 1, which I will call classical limit, right? So you write Q is e to the minus epsilon, you send epsilon to 0, you exponentiate the product, it becomes exponential of an infinite sum, which you can work out, right? And you resum it, and finally you find that there's a dilogarithm popping out, okay? So it's a sort of quantum version of the usual dilogarithm. So that's why the name. Okay. Now another name is quantum exponential. So why is it a quantum exponential? And here you're going to recognize something you've seen in Kilian's talk. So the inverse of E of z actually can be expanded in power of z. So it's very simple. And the coefficients are just Q deformation of 1 over factorial n. So I also note it by n factorial q, but as you can see, it's slightly different. I don't have a denominator. Here I just have the usual Pochhammer, right? Okay, and you can actually write the coefficient itself in terms of a function, right? Because if you think of the infinite product here, and you write z equals some power of q, and you divide by the same thing, but with z equals q, then it will only have finitely many terms which are different in the two products. And so they cancel out, the infinite number of higher order terms cancel out, and you end up with this. So the actual coefficient is a specialization of the function itself. Okay, all right. So now quantum exponential is one other term that's used in the literature, but you can also think of a Q gamma function, in fact. Why? Because it satisfies this gamma function-like identity. If you shift multiplicatively the argument z by q, all you are doing is stripping the function from its first term. Okay, so this is very easily seen here. If I change z into qz, it's like n goes to n plus 1 here, right? And so if you do the ratio with a function in which you haven't shifted it, you're left with only the n equals 0 term, which is 1 minus z. Okay, so it's this relation. Okay, and actually just this relation, which is completely obvious from the definition, this one is a little less obvious, but you can prove this one very easily. Let's say I want to prove this, so I assume it's true, and I'm just writing 1 minus z times 1 over z by using this formula, right? So I get this. And this difference here, I can think of it as, there's this usual trick with series, which is to do just like with integrals, which is the integration by parts, right? But the discrete integration by parts, it's the able summation. Right, yes. Call it whichever. In France, we learn Abel. Okay, we call it Abel. So discrete integration by parts. And then, of course, the difference between these two terms is a power of q divided by the Pochhammer. And so you get the shift. Okay, so very simple relations. So everything basically boils down to this product formula. That's good. And so now let me show you a little bit more about this function. There's what's called a q-binomial formula, which is about ratios now. Right? So you take argument tx divided by the same function but of argument t, and this is the result. So it's again a sum, right? So if x was equal to 0, this thing would disappear, right? And this thing would disappear, and I would just have a previous formula. But now it decorates the formula with a Pochhammer of x. So Pochhammer of x is just the shifted product of 1 minus x, 1 minus qx. And again, it's expressible in terms of the dialogue itself, right? As a dialogue of x divided by dialogue of x shifted by qn. All right? So how to prove this? I think the proof is useful because it introduces you to a new concept here, which is to consider functions not just of scalar variables, but of operator variables. Okay, so what we're going to do is stick operators inside these functions and see the results. So my operator is very simple. It's what I call the shift operator in the x variable. So if you have a function of x, the action of this operator is just to shift, to multiply x by q. Okay, so operator of multiplication by q. And what's the major property of this operation of multiplying x by q is that if I consider the product 1 minus x times this operator t, and I take the nth power, well, what happens, you see, I want to push all the t's to the right, right? I want to normal order this thing. But whenever a t goes across an x, it multiplies it by a q, right? So the first t crosses everything to its right, multiplies them by q. The next t does the same, multiply everything by q, etc. So you can see very, very easily that the Pochhammer is produced in this way. First term is not shifted, second term is shifted by q, third term by q squared, etc. Right? Okay. So this property by itself, well, it's sufficient because you see, all I want is to understand where this Pochhammer of x comes from. So now I just have to take the previous formula, but in the previous formula, I will stick a z, which is not just t, but t times 1 minus x times big T, so that this produces this thing in the series. Okay, so let me explain. So the result will be that if I act on 1, of course t acting on 1 is shift the x variable by q, but 1 is a constant, so it doesn't depend on x. So shifting by q is just acting by 1. Okay? So if I act on 1 on this side, I claim that I create this ratio precisely, or this series. Okay? So let's just multiply by the inverse of that and check that we get 1. So I multiply by the inverse, right? This series. And if I do that, if this was an identity, it would just mean that, well, this denominator multiplies this denominator here, therefore it's the inverse of their product in the other direction, right? And the E of t commutes with everything, right? This t acts only on functions of x. So I can say that instead of acting on 1, I act on E of t. Okay? So this is certainly an identity which is equivalent to this one. But here I notice something very interesting. I've written this as a product of two terms, but inside this term I have t, and this time inside this term I have x. So now I have two arguments that have a q commutation between them, right? If I take one argument and cross the other with it, I will multiply it by q. Okay? So this is a very important remark. And actually there is a way of understanding what happens to this e function if I have two variables which have this property that if you take one across the other, it multiplies it by q, right? And the result is that there's an addition formula. So that's really why it's called a quantum exponential. It's because it has the property of the exponential. The product of E of u by E of v is E of u plus v. But that's only if u and v have a q commutation, a very specific q commutation. Otherwise, it's not true.
But this is not symmetric. So
it's not symmetric.
So how is your equation symmetric?
Aha, but it's not. The left-hand side is definitely not symmetric. Huh? Because u and v, you cannot interchange them, right? They have a q commutation, but in the other direction it would be a q inverse commutation.
Right? So this appears in the paper of Guttheim-Massen.
Many people. It's a very yeah. It's a okay. Personally, I saw that maybe first in papers by Faddeev, in fact. Faddeev. And Faddeev invented another version of his quantum dilogarithm, which has even better properties, but we are not discussing this today. Okay, so I want to prove this for you, just by elementary. This whole thing is about proofs of elementary relations by elementary means. Okay, so I felt like at the end of a conference. At the end of a conference, we can't take any more difficult things, so we just do these sorts of things, right? Little exercises. All right, so let me just prove it, but by the inverse, right? So I want to write the inverse of this thing, right? So 1 over E of u, E of v, and of course it's the inverse of v times the inverse of u, right? So, and I write the two summation formulas for the two inverses, right? Remember, it's the inverse which is nice and clean. So product of the two inverses gives me this, with v first and u next. And then you see in the denominator I have this Pohammer n of q and times Pohammer m of q, and this is actually the 1/3 of the formula for the q binomial coefficient, right? So I put the q binomial coefficient, and now I have to divide by the thing I put by hand, right? So now I have 1 over Pohammer n plus m of q binomial times vn times um. And if you ever played the game of normal ordering two q commuting variables, this is the formula for u plus v to the power n plus m. It's the sum over n of q binomial, right? So if you fix n plus m and you sum over n, let's say, well, this summation here just produces for you this power. So now I have u plus v to the power n plus m divided by Pohammer n plus m. That's exactly 1 over E of u plus v. Okay? So that's your relation. Inverse of this is inverse of this. So now let's go back to the previous case. I told you, here we had something interesting. We had two guys which q commute. So if the two guys q commute, I know that their product of e's is the E of their sums, right? So I just use that. But the sum, u plus v, I can rewrite as another sum, u prime plus v prime, right? By rearranging the terms. I can do that. But I can also arrange myself for these two new terms to still q commute, right? So that now I can take them apart again, right? So out of two terms, a product of two terms, I put them together, I take them apart, I can rewrite them as a product of two other terms, right? This is really a nice trick that you can do thanks to this addition property. Okay, so once I've done this, let me rewrite the first thing we were computing. We expressed it in this manner, and now we have expressed this product of two in terms of a product of two different objects, right? And now I can act on this E of t, but now this guy comes on the right, and he only has t. And so again, t acts on x only, and there's no function of x, so t acts as 1. So E of t inverse on E of t gives me 1. Now I act with this beast on 1, but now, again, t acts on 1 as 1. And there's a 1 minus t in the argument. So the first time it acts by 0. So all the terms are 0, except the terms where the argument doesn't appear, which is 1. So you get 1 as an answer, and that proves my identity. So from this little set of tricks, I ask you to remember one lesson, which is that using non-commuting arguments can be really useful. Okay, so that's first thing. So this quantum dilogarithm satisfies more identities. So if you're familiar with a dilogarithm, it has a 5-term identity, famous five-term identity. There's also a 5-term identity for this quantum dilogarithm. So again, it has to deal with variables which q commute with each other. And so u and v q commute. And you see, it's just a way of interchanging the position of this u and v, but you can do that only at the cost of having a third term in between. Okay, so that's this pentagonal equation. And I claim that the pentagonal equation is a direct consequence of this, in fact. So you just have to write things in the correct way. Okay, so first thing you remark is that the product of these two terms, because u and v q commute, right, here, is also the E of their sum. Okay, so the E of the sum is like this, because I can write uv as vu times q, so the q inverse goes away, and then I get this. And the E of u is here. Now I'm going to multiply to the right by 1 over E of u, so that I expect to see only E of v on the right. Okay, so this identity should boil down to this identity, completely equivalent. So we want to prove this identity, but as usual, E is not nice, but 1 over E is nice, right? So on the left, I have conjugation of E by E of u, and on the right, I have just an E. So conjugation of some guy is just the conjugation of the inverse is the inverse, right? So I'm going to compute the conjugation of the inverse. So let's do inverse of this guy times 1 over E of u. For the inverse of this guy, I'm using the formula, right? The summation formula right here. The E of u, I leave it like it is, okay? And now, what I notice, again, I'm using something we said before, that when I have a product like this to the n, I can put all the v's to the left and all the 1 minus u to the right, but each of the u's on the right will be shifted accordingly, and I'm getting a Pohammer here, right? So I have v to the n on the left and Pohammer n of u on the right. But Pohammer n of u is just the n first terms in E of u. So what's left is E of shifted u. Okay? All right. So now I want to conjugate. So I want to multiply by u on the left, E of u on the left. So I have this same thing here. And now there's E of u on the left and 1 over E of qnu on the right. And this Vn here, it's very easy to see that if I take this E of u across the Vn, it will be shifted by Qn. So it will cancel this guy. So actually these two guys cancel. And so I'm ending up with 1 over E of v. Okay, so that gives you the pentagon equation with very little calculation. Okay, so now why am I showing you all this, right? It's because I want to use it, of course, to describe these Macdonald functions. So let me explain what those Macdonald functions are. So first I have to explain Macdonald operators, of which the Macdonald polynomials are common eigenfunctions. So it's a family of, so for an minus 1, right? It will be a family of n operators which act on functions of n variables. All right, and here are the operators. So they depend on A. Think of A as their degree or their order, rather, because it's really like differential operators, but they are difference operators. So there will be a linear combination of a bunch of shift operators. So remember, this notation was for shift of a xl variable by q, meaning that when it acts on function of a variable xl, it multiplies xl by q. Okay? So I sum over subsets of cardinality A. That's the order, right? And so for all the elements of these subsets, there will be a shift of an x in F, right? So I have A shifts for each term in this summation. And then it's a linear combination, and the coefficients are kind of ad hoc. They are expressed as rational fractions involving x and the parameter t. So there's two parameters in these Macdonald polynomials, Macdonald theory, which are q and t, which plays very, very non-symmetric role, as you can see. But there's the symmetry which mixes them up, as we will see later. Okay, so I have these order A shift operators, right? Among them, the largest A is n. So if A is n, you see I is everybody. And so there's no j, right? Because j is outside of I and inside of 1n. So there's no j, therefore no product here. And I end up with just the shift of everybody, right? So this operator actually is part of my family of Macdonald operators. You can add up one more, so the A equals 0, which is just kind of trivial. It's a convention. D0 is 1. The theorem is that these D's commute with each other, right? So I have a commuting family of difference operators. Okay, so very standard theorem. And there's a very nice proof that you can come up with in a few lines if you first read Cherednik's books on Daha, which might take a while. All right. So the Macdonald polynomials. Okay, so we have a family of commuting difference operators. So it's natural to ask a question about their eigenfunctions. And these Macdonald polynomials are actual monic polynomials, right? Which are indexed over, their degree is indexed by some integer partition, so n integers ordered, right, non-negative, in such a way that they're common eigenvectors of all the dAs that we've described before, and the eigenvalues are given by elementary symmetric functions of order A, right, of these variables S, which are constructed out of the degree, lambda, right, the parameter q and the parameter t. So this you might recognize as being the longest root of the A-type algebra, right? So rho I, if you want, but it's just an integer power of t, which changes with every index I. And here you have q and I. You see, the indices are not symmetric because the permutation is ordered like this.
What the harmonic in which variable the harmonic?
Monic, it's because there's a, you see, you order the terms. This is the polynomial of several variables, right? And so you're deciding that the term which has these properties, x1 to the lambda 1, x2 to the lambda 2, xn to the lambda n with this property, is the actually top degree term, right? And so the coefficient of this is 1. So if you fix the coefficient of this term to be 1, it fixes the overall normalization of your eigenvector. So it determines the polynomial uniquely. Okay? So the monic just means coefficient 1 of this leading power of x.
And the other powers are less in some sense?
Well, it's going to be a symmetric polynomial. So actually, this power carries with it an orbit, right, under the symmetric group. So it's actually a monomial, right? I mean, it's called a monomial function, but it's a sum of monomials, right? Which is symmetric with coefficient 1. And then the rest is going to be lower with respect to a certain order, which has to do actually with how I define my functions. So if you wait a bit, you will see it becomes very clear. Okay, and so these are these elementary symmetric functions, their eigenvalues. Okay, so it's, and actually you only need D1 because D1 is enough to determine completely the P lambda, but it's nice to know there's a whole family. Okay, now these polynomials themselves, there's a whole literature on their combinatorics. They have various versions which are more suitable for combinatorics, like modified Macdonald polynomials, etc., which are essentially polynomials to which you apply platisms. But we are not going to enter into this. We are going to concentrate rather on the difference operators and on the solutions of the difference equations, which are not actually polynomials, but series. Okay. So just another thing is that these polynomials, they also satisfy a set of dual equations, as many, right, which are also indexed by a's from 1 to n, and which express, so they're called Pierry rules, they express how to multiply a polynomial by an elementary symmetric function, right, and re-express this in terms of the polynomials themselves, but shifted with slightly different degrees, right? So, and here is the explicit form of this operator, Pierry operator, and you will see why I call it H. So this Pierry operator looks like this. So again, it's just a product of shift operators, but now in the variables S. So if you remember, S was actually a compact notation for a sequence of Q to the lambda, right? And so shifting an S by a Q just means shifting a lambda by a +1, right? Changing lambda into lambda +1. So we are multiplying the polynomial by something of positive degree and re-expressing it as a combination of the same set of polynomials, but with degrees slightly augmented, which makes total sense. Huh? And the coefficients are these. All right. And so I call them commuting Hamiltonians because of the later interpretation, right? So, but they are definitely commuting operators, but now instead of acting on the x variable, they act on the s variable. Okay. All right. So,
is it an example of Roisenard's duality in some sense?
Yes, yes. You will see all the duality. There's more than that even. Yeah. Definitely. The x and s variables now play extremely symmetric roles, yes, for type A. All right, so now what we're going to do is look for series solutions of the Macdonald eigenvalue equations, right? So we had these eigenvalue equations, but now we will demand that these series converge in certain sectors, and here the sector will be where the xi plus 1 over xi are less than 1, right? So you order your variables, x, and you're considering a series in the sector when these x's are ordered. And this series is going to be a power series in these variables, basically. And so you need to kind of start the machine by a factor which is symmetric in x and s, and which will play the role of this top degree, right? So when we're going to specialize this thing to s related to some partition, it will behave like x to the lambda, right? But now s, I'm asking you to think of the lambdas to be complex numbers, right? So the s variable becomes an abstract variable just like x. Okay, so we forget about these integer partitions that were labeling the degrees of the polynomials. And sorry?
The parameter t, what is this? This comes from not permutation group, this has come from another group, sign permutation.
T, what do you mean? No, the T, okay, so if you go back to the DAHA, double affine Whittaker algebra, you have two essential parameters. Things happen on a torus. So Q has to do with periodicity around the torus, right? And T has to do with eigenvalues of the break group elements, Okay, so you have eigenvalues on one side,
Thank you.
and
Great.
okay,
I think there should be some another.
right. But there's a symmetry. You can interchange Q and T, which is very non-trivial. Okay, all right. So Q and T here, you can see them again, right? So because of this term now, it decorates a little bit. Each shift term is going to take things out of this power here. So some S variables are going to pop out. But so for each T, there is an S variable. Okay, that's the only difference. And I'm writing essentially the same identity, eigenvalue equation. And I demand that F be a series of those, a power series of those guys, which starts by 1, right? I normalize it to start by 1. This 1 is like my polynomials were monic, right? So it's the 1 coefficient. Okay, you could ask, all right, interesting, but what have we gained, right? So here I'm calling this operator, as it's decorated by this, I can't call it dA anymore, so I call it dA of XS. All right, so the facts are the following. So first of all, out of this whole set of equations, I only need the equation A equals 1. All the others commute, so they're all compatible, right? And so A equals 1 gives me enough information to determine F uniquely. And why? Because the equations, if you look at them carefully, the fact that F has an expansion in these variables, and the fact that I can expand all those coefficients in these variables as power series, if you want, shows that the equation itself is triangular for the coefficients of those various powers. So actually, F is determined as the unique solution of a triangular system. Okay, it's as simple as that. Okay, now second property, which is much more interesting, is that F actually contains the information on all the Macdonald polynomials. So you have one series and it contains information on all the Macdonald polynomials. All you have to do is specialize this variable S, which was kind of a dummy variable, right? You specialize it to some specific power of T times specific power of Q related to an integer partition, right? And then some miracles happen. Exactly like in the talk of Kilian earlier, he mentioned that some of these series truncated into polynomials, right? So the same thing happens here. Because of the form of the coefficients of this series, it will truncate to a polynomial, okay? And now this polynomial multiplied by the prefactor that we have, once it's specialized, produces the Macdonald polynomials, okay? So any specialization of the series corresponds to a Macdonald polynomial of this form with integer partitions, corresponds to a Macdonald polynomial.
Can we see when there is a constellation which makes a...
Yes, I'll show you the SL2 example. Everything will be clear. Yes, yes. It's kind of very non-trivial a priori, but you will see a posteriori it's very simple. Yeah. So F has a very nice expression, actually, due to Shiraishi and Numi in 2011 in a paper that was never published, I think. But, okay, Numi died this year, so I think it's time we know about this paper. Okay, and what they show is that this F function has a sort of Q hypergeometric flavor, and I will show it later. So now, there's another remarkable fact, which is that this Macdonald function is actually related to the Nekrasov, so-called Nekrasov functions for supersymmetric gauge theory, right? So some very specific case, adjoint matter, etc. Okay, and this has been the subject of many papers involving Shiraishi and various people, say in the last decade. All right, and finally, there are dualities. So that's what was mentioned here, and we'll explore them. Okay, so yeah, so the same thing as we said for the Macdonald eigenvalue equation, we can do the same for the Pierry rules, right? So same story. We have an equation like this for F, but now H has to be decorated. But now, as these are shift operators of S, when they multiply, when they act on this prefactor, a shift operator in X will pop out an S right? An S to some power, right? So a shift operator in S will pop out an X, and therefore now I'm decorating my Hamiltonian. Here there was nothing, and now there's a product of X and 1 for each shift operator in the variable S. It's a very simple decoration. So again, instead of calling it HA, I call it HA of Sx. Okay, so we have all these equations. Finally, the example of SL2 where you will see what happens. So here is the first Macdonald operator for SL2. Here I'm writing gamma because I prefer to keep the letter T for the S variable. So for the X variable, I will call it gamma, right? So gamma 1 shifts X1 by Q, gamma 2 shifts X2 by Q, and you have this operator. And so here is the action on the function, right? So I'm writing, I'm using, there was a denominator here and here, which I put here, right? This is the eigenvalue, and this is the eigenvalue equation for my series. Okay, so the series here, I put x1 to the lambda 1, x2 to the lambda 2, which has to do with this prefactor here, right? So here the big F is the small f times this, right? So this is what I called small f before. So that was the equation for big F, but now for small f. And so small f I can expand in power series where xi plus 1 over xi is just x2 over x1, right? So I'm really in the sector where I imagine that x2 is smaller than x1, right? Okay, so this ratio is small. So I expand in power series, coefficient Cn. And now, well, you plug this into this, right? And you find that there's this, okay, triangular system is really a very big name for a recursion relation, which tells you what Cn is in terms of Cn minus 1. Huh? So you calculate Cn, right? And you find this very nice product formula. And this very nice product formula, I can rephrase it in terms of Pohammers. Okay? So Pohammer of T index n, Pohammer Q index n, and then T times S2 over S1 index n, Q times S2 over S1 index n, and finally some extra power of Q over T. Okay?
It's a standard Pohammer, right? So
yes. So no, these are Q Pohammers. I'm sorry, these are Q Pohammers.
So this doesn't matter because the denominator.
Yeah. But the definition is the one I gave before, right?
Denominator you forgot. But this is,
Okay, so it's. Let me write it down.
You can think as a gamma function.
What I call x index n is the product of 1 minus q I x, I equals 0 to n minus 1. That's the Pohammer for me. Q Pohammer.
And your last formula here, is it what you mean by having a hypergeometric flavor in the work of...
Yes, absolutely. Okay, so very good. So here is the function, right? And the function is a 2f1, right? It's 2 phi 1, but q hypergeometric 2 phi 1 of these three parameters, t, ts, qs. I call s the ratio s2 over s1 and x the ratio x2 over x1. And the argument is, involves q over t. So the Macdonald function for SL2 is a q hypergeometric 2f1. Okay?
But your SL2 is the quantum SL2. It's not classical SL2, the algebra.
Oh, it's Macdonald polynomials associated to A1, right? So A1 Macdonald polynomials, depending on Q and T explicitly.
Equal 1 is okay, but no. That is quantum version, yeah?
Yeah, but the Macdonald polynomials are already quantum. That's my point, right?
I see.
Because they solve difference equations which themselves have some quantum nature.
Yeah, but
okay?
only one parameter Q, this is quantum.
No, they have Q and T.
Q and T.
Q and T.
So T is important.
T is different parameter. Okay, so we have this series. Now, to answer your question about why do I get a polynomial when S specializes, maybe I I'm sure I say it later, but let's look at it right away, right? So you remember what I want to write. Let me just use my pen. It's easy, right? I want to write S1 is t to the 2 minus 1, which is 1, times q to the lambda 1. And S2 is t to the 0 times q to the lambda 2, right? So S2 over S1, which is S, has to be t inverse q to the lambda 2 minus lambda 1, which is an integer which is negative or 0, right? Now I take this value of S, t inverse q to the negative integer, and I stick it in here. So the t inverse cancels the t, and I get a q to the negative power. Now a q per hammer, if I stick in it a q to the negative power, is going to be 0 as soon as n reaches the power, right? And so that's a truncation. Okay, so you get a truncation of your series into a polynomial. And those polynomials are the Macdonald polynomials for A1. Huh? Okay. All right. So now I want to here comes the quantum Dilogarithm. Okay. So why did I bother you with quantum Dilogarithm in the first place? For this reason, is because I have a way of representing the Macdonald function in terms purely of quantum Dilogarithm, but having learned the lesson that we should consider quantum Dilogarithms of operators, I'm expressing it as a ratio of quantum Dilogarithm of some operators acting on the constant 1. Okay? And this is the formula. All right? So it's almost obvious, but I will show it. And I call it Mellin-Barnes. So some people might object that usually the Mellin-Barnes representation has to do, first of all, with not with quantum stuff, but with actual stuff, which involves gamma functions instead of Dilogarithms. But I showed you that you could think of a Dilogarithm as a quantum gamma function, right? So far you can believe me. But then I have no integral in here, right? But I have these operators, right, which shift by q. And if you think a little bit about it, the Mellin-Barnes integral has to do with collecting residues and summing over them, right? And what we are doing here is kind of equivalent to that, but in the Q world, in the Q-deformed world. Okay. That is, series involving Q are actually sums over residues at powers of Q, something like this. Okay. So I call it a Mellin-Barnes formula. So now here in there, you see the purple T, Q commutes with the purple S, right? So T and S are in a world, and X and gamma will be in another world, right? So these are two quantum tori that don't talk to each other, that is, that commute with each other. Huh? Okay. So why is this? So let's use the first formula, the binomial formula that I showed you before, right? So that's where it's important to have suffered a little bit to prove them, because now we remember them. So this one here, I'm going to put inside B equals T. Well, what is B? It's the ratio of what I see above and what I see below, right? And here what I see above and what I see below, their ratio is in fact this T, right? So B is going to be equal to T. And for A, I put the rest, which is this complicated rational fraction, right? And so if I compute the action on one of this ratio, well, I use this formula with A and B like this. So B appears here, right? This is A, and this is the sum, right? And I'm supposed to act on one. And now same thing as before, right? I want all these T's to be put to the right, so that when they act on one, they act as one, right? So, but whenever a T crosses a thing like this, it shifts the S by Q, right? So on the numerator and the denominator. So what I get as a result is a ratio of Q per hammers. That's it, right? Because the numerator creates a per hammer, the denominator creates another one, so I get a ratio. And then I act on one, and I get one. So I get this function, and that's exactly the function I had before, right? So yes, you can rewrite this 2f1 hypergeometric as just the action of a ratio of Dilogarithms on the constant one. But, okay, you could say, okay, nice, but why? Why do this? Why do this? Because we can prove many things using this. And because we know exactly what this E obeys, right? A very small number of identities, right? So you want to prove anything, you have to resort to those identities, okay? And that's it. And everything becomes purely algebraic. Okay, so for instance, there are these dualities that were mentioned. That is, you can interchange the roles of x and s, right? So the function that I showed you, that I introduced of x and s, you can actually switch s and x in this function at the expense of a product of dilogarithms. So we are still in the example of SL2 because I think it's better to see how everything works with SL2 before going to SLN. Huh? So this duality is called bispectral. Well, you remember we had a difference equation, a Macdonald eigenvalue equation, acting on x. But there was the Pierry equation acting on s, right? But now we understand that the Pierry equation acting on s is just the conjugation with a certain function, which is simple, of the same equation in which I have interchanged x and s. That's it, right? So my Pierry operators are actually conjugates of the Macdonald operators. Okay. Now there's a second duality, which is much more intriguing, which is called Poincaré duality in the literature, and has to do with geometric interpretation of Macdonald polynomials in terms of stacks and various abstract objects, which I have no time to explain. But this duality actually interchanges T and Q over T. Okay, despite the fact that they appear in a completely different manner in the problem, you can actually interchange them. Okay, at the expense again of some ratio of dilogarithms. Okay, so just as an example, I'm showing you the proof of bispectral plus Poincaré. That is, I'm combining the two, right? So I'm expressing this guy in terms of this guy and then in terms of this guy, right? So, and here is the proof. So the first function we know is this, and the one we want to arrive at is the same, in which I have interchanged st with x and gamma, and in which I have interchanged t with q over t. So q over t with t, and t with q over t. You see that? And this is just the prefactor that my previous identity is predicting. So let's see how to prove this thing. So the first thing here is to realize that I can multiply by the inverse of this. It's a function purely of x. So when I multiply it on the left here, this is just a function that acts on s. So it doesn't see x. So I can put the x dependence on the right. Okay, so it makes things a bit more symmetric. All right, next thing is the following. This has t, and this has x, and this has s, and this has gamma. But xt and s gamma, they commute. Okay, meaning that the arguments of this function here and here, they commute with each other. So I can actually multiply by the product of their inverses and cross them, right? So send this guy to the right and send this guy to the left. Okay, that's what I'm doing here. Okay, so I have interchanged the two guys. So we're almost there. So now, the only question is that I want now to commute. You see, now I have a gamma which has a non-trivial commutation with x. And all I want to do is to commute this term outside, right? And on the right-hand side, I want to do the same. I want to commute this term outside. But when I do that, look at this. Gamma is a shift of x by q. So when it acts on a dilogarithm, it strips it from its top term. You remember that? The gamma function property. So if I have this already in factor of gamma, it's going to be killed because this is the first term of this guy and this is the first term of this guy. So if I cross the gamma with those guys, they're stripped of their first term, and now I put it back. So it gives me the ratio, and this fraction has disappeared. So when I commute these guys through, I kill the fractions that are in front. So what I'm ending up with is something very simple, is this. Okay? And now it's over because gamma acts on 1 by 1, right? T acts on 1 by 1. And so you end up with this identity, which is obvious, which is symmetric. Okay? So that proves the duality relation just by using the Dilogarithm. Okay? Alternatively, of course, you could have opened the books on Q hypergeometric functions and seen that there are such things called Heine transformations, which you can apply. And so you have 3 of them, H1, H2, H3, and it's not very difficult to see that H1 can help you prove bispectral duality and H3 Poincaré duality. Okay? So that's another way. All right? So there's an interesting limit, which is called the Q-Whittaker limit, in which the polynomials become Q-Whittaker polynomials, right? And the functions that we've been considering become Q-Whittaker functions. Okay? All right. So Q-Whittaker functions are just Q deformations of the ordinary Whittaker functions that you have, you can define in Lie theory, right? Very standard objects. So this limit is just sending t to infinity. So, but we have to be very careful because you remember that this s variable in the polynomials, right, had a t dependence, right? So in particular, what happens to the eigenvalue of the eigenvalue equation for Macdonald polynomials is that you're extracting the leading term only. And so only one product of S is coming out, right? If you extract the top power of T. So you're kind of destroying the nice structure in which there was an elementary symmetric function and replacing it by just the top term, okay? Now, the operator itself, it's not so bad because it really keeps the same structure, except that the term that had t now is blown out, and the term that didn't have t disappears because t goes to infinity. Okay? And then there's the Q-Whittaker universal series, which is the universal solution, right, or called also Harishchandra series solution, of now the t going to infinity Macdonald equation that we got by taking the t infinity limit of before with this property of series expansion, and so it has the same, exactly the same definition as before, but in this t going to infinity limit. So why the name Q-Whittaker? Because the Pierry rules turn out to be the Q-Toda equation, so the non-relativistic Toda equations. Okay, introduced by Ettinghoff, let's say, for SLN. And so the Pierry operator becomes what's called the open Q-Toda Hamiltonian for SLN. And this is the formula which you will recognize. So this is the H1, and you probably can recognize it from Ettinghoff's paper on the subject. Okay, so the HA infinity are a commuting family of higher Hamiltonians, commuting with these basic Hamiltonians of a Toda, Q-Toda equation. And when Q goes to 1, if you send Q to 1 in the right manner, you recover the differential Toda equations. Okay, so we're still in the example SL2. I just want to show you what this Whittaker limit looks like. And if you remember the talk of Kilian, right, he had also some terms with quadratic powers, right? Instead of Q, he had something he called theta, right? And so I believe there are really connections between what he was telling us and this. Okay. So this comes out because you're sending t to infinity, right? So in a Q-Power hammer, if you send the argument to infinity, you have to be careful. You're blowing out the term on the right, right? And so you have all these powers of Q that pop out, and that's what creates for you the quadratic power of Q, right? Okay, so, and I call sigma just the limiting version of S, right? So S is T inverse sigma. Right, and this is no longer a Q hypergeometric, so it doesn't have as many nice properties. But there is still this property that when you specialize sigma, you get the Q Whittaker, now polynomials, which are the t going to infinity version of Macdonald polynomials, and they have a particular simple form for SL2, is just a Q inverse binomial coefficient, the coefficient of xk. And if you want the full polynomial, then you have to multiply by x1 to the lambda 1, x2 to the lambda 2, and take n to be the difference, lambda 1 minus lambda 2 of x. So this is a polynomial of x which starts with 1, and this is the actual polynomial of x1, x2, which is symmetric in x1, x2. Okay, so this guy has a quantum Dilogarithm expression just by taking my previous expression and sending t to infinity, right? E of 0 is 1, right? So only one E, the E in the numerator survives, and it gives you this super simple formula. So actually, this thing here, which looks complicated, is just this, okay? And from this, by the way, from the identity that we've been using now several times, E of AB over E of A, you can take A to 0, which removes the denominator, and AB fixed, so B to infinity and A to the 0 at the same time, AB fixed, and you will get this identity here, right? So all these coefficients here, including the Pochhammer, are just the coefficient in the expansion of E, and now we understand that this is just coming from this product here. So it's all nice and good. All right. And so the Hamiltonian equation that we had before, right, is the open Q-Toda equation for A1. I can write explicitly in terms of T, which is the shift of a S variable, right? G is my Whittaker limit of Macdonald function. And you can actually have a direct proof of this eigenvalue equation, right? Toda equation. So G is explicit, right? It's a Pochhammer of something, Dilogarithm of something acting on 1. And you can already see that the argument here appears here. So well, okay, so maybe it's too late, so I'm going to skip the set of tricks, but there's again a set of tricks to prove this directly, just in terms of the Dilogarithm. So, okay. So the lesson 2 here is that the presence of this Dilogarithm all over the place actually allows to formulate purely algebraic proofs, which is a big improvement compared to what's been done so far.
C'est quoi what is the contrary of algebraic proof in those cases?
So, all right. So, okay. So you have to basically, well, okay. So one type of proof would be by identities, right? So you want to identify coefficients in various series, right? And usually it involves summation formulas, complicated summation formulas. So this kind of removes all these things from the landscape, and you end up with just using 2 or 3 properties of the E, of the Dilogarithm.
And this for you is algebraic proof or non-algebraic?
Yeah, that's what I call the algebraic proof. Yeah. All right, so that's the general SLN case. So in this paper of Shiraishi and Nomi, they write an expression for the an-1 Macdonald function in this form. So again, expressed in terms now, instead of just the variables xi plus 1 over xi, which you can think of in terms of the Lie algebra as roots, right? Simple roots. Now it's positive roots, right? Because it can be it's no longer j neighbor of I. It can be distant, right? So the number of summation variables, so you sum over integers, theta ij, which are in a triangle like this. So you can think of them as having to do with Gelfand-Zeitlin triangles, for instance. So you have a summation of a triangle of variables, a product of these powers of those variables, right? And then coefficients. And the coefficients themselves are completely factorized. And they take the form of Pochhammers with indices. Before I had n, but now what plays the role of n are all these variables in this triangle of summations. Okay? So, theorem, the Fn expressed in this way is the Arjichandra series solution to the Macdonald equation for SLN. Okay, so I call it Q hypergeometric on steroids because it's not only Pohammer.
Last line.
I'm sorry. Q hypergeometric on steroids.
Okay.
Yeah. It's stripping the last line. Ooh, I hope it didn't do that before.
Okay.
All right.
Just this time.
So, okay. So the thing is, why on steroids? It's because there are all these shifts with powers of Q that you don't usually have in Q hypergeometric functions, right? So there's something going on here. Okay. There are dualities. So now, instead of just a ratio of two dialogues, you have a triangular product, right? Everything becomes a triangle. Right, so a triangular product of like a sort of van der Monde, if you want. So call it delta, just like the van der Monde. And now the bispectral duality is delta of a variable s times f of a variable xs is delta of variable x times f of s of x. So again, you can interchange x and s variables, and you still have a Poincaré duality, but now you have to divide f by the delta, right? So f divided by this delta is equal to the other f divided by delta, and this is the guy which is invariant under t goes to q over t. Okay, so here is a first remark. You can rewrite, okay, this is technical, so you have to believe me at this stage. You can rewrite the various terms in these products by taking some terms out and rearrange it a little bit. And so this rearrangement here, which I copied here, is just to remind you of what this particular ratio of dilogarithms look like, right? It was a sum over t Pohammer n divided q Pohammer n, q over tx to the power n. So here what we see is exactly the same thing, but with the thetas, right? So here there's a missing product over the thetas, right? So it means that every single summation in this triangle of summation I can replace by the action of a ratio of dilogarithm operators, okay? And then you will ask, what about all these powers of Q? Well, these powers of Q have to do in which manner am I ordering this product of operators? Because now these are operators, they don't commute, right? So you have to put them in a certain order. And of course, a t somewhere on the left is going to act somewhere on the right. And when it acts, it multiplies the variables s by q. So all these powers of q are going to come from action of t's that are on the left. Okay? So if you order the things in the right way, you can reproduce entirely the Shiraishi-Numi functions. So that was what we did. But here, I put a question mark because it's not quite true. This is wrong, but it's not very wrong. It's only wrong in that it doesn't produce these terms here, right? So it's almost right, but not quite. And the trick, it took a while to figure it out. The trick is to just introduce new variables which allow the shift operators to not just act on the right, but also act on the left. So how do you make an operator act on the left? Here is the trick. The trick is you write an integral with delta function, right? So you have t, which is unfortunately on the right of a function of s, right? And you would like to act with this t on this function of s. You introduce an integral over s prime, and you put a delta of s prime minus s to the right. So when t acts on the s, it transfers its action to the s prime, which by the delta function after integration transfers it to the left. Okay, this is the trick. So now we have an integral formula for the Macdonald function. That's it. Okay, so there's a rank recursion, just a direct consequence. Here I had a product from a equals n to 2. So if I just write the a equals n term, I realize that what's after is just the function of rank 1 less with 1 less variable, right? So this is very nice. It gives you a rank recursion. And by the way, this is the general Mellin-Barnes relation for Macdonald functions. Here is the example of SL3. I don't know if it makes it nicer, but at least here you see all these complicated parameters with some sporadic powers of q, right? And here is the formula that reproduces this, and it needs one integral so that this TS2 inverse can act retroactively on the S2, which is on its left. Okay? And here you recognize the rank 1 less, which is the SL2, whereas we were expressing the SL3 guy. Okay? So the Macdonald polynomial, same story as before. This kind of specializations with lambda and integer partition is going to give you the Macdonald polynomials. The finite truncation of a series, let's look at SL3, for instance, right? So we're saying that S3 over S2 is T inverse Q to the negative power, and S3 over S1 is T minus 2 Q to a negative power, right? So if we stick that in the various terms that we have here, these two terms are going to create a truncation in the N1 variable, and then you're going to also have a truncation in the N2 variable because of these two terms. And so everything truncates finitely, and you will get a polynomial again, right? So, and you can do the same analysis on the general formula. There's also a Q-Whittaker limit. So everything works the same, right? And so the open Toda equation you can write in this way, and you can prove it because the Toda function, so the nice thing when you send t to infinity is that you erase all the denominators, and at the same time you erase, see here there's a t in denominator, so t goes to infinity is going to erase this guy which I needed to retroact on. Now it's no longer there. So I just have a product of dialogues. That's it. So to prove Toda equation is just one line. Yeah? You just have to show that this product of three dialogues satisfies this equation. All right. So that's the general Q-Whittaker limit. Okay. Right. Rank recursion. And the epilogue, I don't think I have time to do it, but there's a connection of all this with cluster algebra. Right? So the quantum Dilogarithm is the main character in quantum cluster algebra. And to make a long story short, there is a certain cluster algebra which is associated to the Q-Toda system that we have found as limit, right? And the way it works is that the operators themselves, right, are actually variables in a quantum cluster algebra. Right? So they occupy the vertices of a certain quiver, and when you do mutations, you evolve these operators. Okay? So you have a relation like this, which tells you how the operators evolve, and the evolution direction, which is you can think of as a time, is actually a decoration of the operators by some powers of x's. Okay, so there's an SL2Z action, which is nice to see within Daha. There's the notion of, and there's a notion in the cluster algebra of dual called X variables. So there's the A variables, which are the Qs I was presenting before, and the X variables, which are expressed in terms of adjacency matrix inverse of a quiver in terms of A variables. And these X variables, they are very nice because they must Q-commute according to the quiver. That is, this guy should Q-squared commute with this thing because it has a double arrow pointing like this. And this guy should Q-commute with this guy because there's a single arrow between them. And so you will see that this choice of T's and S's precisely reproduces the right thing. And the mutation in the quantum cluster algebra are driven by adjoint action of a quantum Dilogarithm, precisely, of these X variables. Okay? So now, if you know exactly which mutations you want to do in the cluster algebra, it will give you a certain product of Dilogarithms. So all these products of Dilogarithms that we've seen before in the Q-Toda version, at least, can be interpreted as mutations in the cluster algebra, sequences of mutations. So one of them would be mutations about all these red dots, and it's called the Den twist. Another is called the Q operator. It's a more complicated sequence of mutations which does like this. It goes through all the diagram. And so this Q operator has a very nice property that it acts on the on the Macdonald function diagonally with eigenvalue, which is just the product of dialogues that would come. Yeah, it's a Baxter operator. Baxter Q operator, absolutely. Okay, and so this is the example for Q Toda, but we have actually a version of this for Macdonald. So I think I'm over time. So here is just the example of SL2. That's the Q operator. That's the conjecture, because we don't have a proof yet, but it will come, that those Q operators commute with each other and that they act on the Macdonald function diagonally with its eigenvalues. Voilà. Thank you.
So comments, questions?
Yeah.
Yes. Why you did not start from the start with SLN?
Well, I could have started.
No, it's a kind of joke. I mean,
Yeah, okay.
formulas, it was obvious.
I must say, I'm still amazed by this paper of Shiraishi and Naomi.
So, more serious questions. So, Macdonald's, in the classical case of for orthogonal polynomial, they are generalization of lower cases.
Yes.
And questions when you go to the Q analog here, do you get for free all the
tower? Yes. Well, you see, Q Whittaker is already a limit, right? It's this T go. By the way, there's two limits. There's T going to infinity and T going to 0, which are kind of dual of one another, right? So you get those two limits very easily. But then you can do differential limits, right? So sending Q to 1, so classical limit. So for instance, the Q hypergeometric become hypergeometric in that case, right?
And there's no cases for which the limit is a problem or something?
Well, okay, my experience is that the Q world is much better behaved in terms of singularities and what's happening. And when you take limits, in particular the classical limit, you can land on something which is kind of not as nice. For instance, confluent hypergeometrics, for instance, right? Which are a bit less nice than the usual things. So I'm happy with the Q world.
And so about let's say call it the Q Barnes Mellin. So the classical Mellin Barnes integrals are a way to prove some identities between poly zeta, multi-zeta values and so on.
Yes.
And natural questions, is there a nice way to generalize Q identity?
Good question. We haven't explored. So excellent question.
And when you mention algebraic computations, it's indeed really algebraic. It's very nice that you can. In fact, it's possible to almost to automatize with computer algebra. In the sense of autonomy theory, you have operators, you have the rules, and in the same sense of autonomy theory, maybe one day we could have some packages which could prove some of the identities.
Possibly.
One question. Do you have a possibility of thinking of Q Meyer G functions?
Meyer G, you have to explain a little bit.
Okay. So, because these are inverse Mellin transforms of products of gamma functions.
Okay.
And here you have
okay, now, but we need a sort of Q-Mellin transform, probably, right? Okay, which one can think about, yes, definitely. Okay, why not? Yeah. Maybe actually in hiding some of the identities we have are already of this type. Yes.
Because Meyer G functions have enormous applications, very down to earth. And well, this is very sophisticated. Maybe if you need some down-to-earth applications of that, maybe we can go through a new kind of a Meyer G function. Right. So there is a possibility of one.
Yeah, I waited for a long time. So I was 25 years old and at one car institute when I met Sergei Kirov. And he teach me this, but not in that case as a from representation theory of permutation group. So my question is now, after 25 years, did you come to, because you know curve diet, so did you can say your result in the representation theory of permutation group? Because Kerov and Wiersik will be very happy, and I also.
It's very close, because actually the permutation group is the Weil group here,
Yeah, of course,
right?
of course.
And
Infinite permutation.
infinite permutation.
That
Okay.
is important.
Well, but you can also consider Macdonald in infinitely many variables by expressing them in terms of power sums, right?
In paper in memoir IMS, he did this, and we use this. This is the representation theory and of permutation group, and so I would like.
Well, what would be really interesting is to see what happens with Daha, really, because the double Affine-Hecker algebra is really the right structure behind this.
But Daha is also not for permutation, only for.
Right, but if you look at spherical Daha, then
No, spherical is the commutative theory.
Right.
You know,
Yeah.
we know this. Yeah. Anyway, it was thank you, beautiful for talk, and now we wait for real application to representation theory of Y group or generally, because this is only permutation group. Yeah, but for B and series is some other parameter will be, I hope.
Okay,
Yeah.
so thank you very much.
Thank you.
The lecturer and all public who asked this question. Thank you.